Hello everyone, welcome to another class, another topic, and today we are going to talk about symbolic execution. Another interesting topic, another topic as many as we have been discussing could be an entire course, could be extended over multiple classes, but today we are going to give a brief introduction over it. Of course, if you really like this topic, if you'd like to know more about this topic, please let me know, we can chat later, or even I can incorporate some more information about this topic on the further classes, right? But today we're going to give a brief introduction on this topic. And the interesting point here is that we have been seeing a progress during the previous classes, right? Because initially we started talking about the case of static analysis that has many advantages, like its speed, its easiness of use, but it lets some vulnerabilities to be undiscovered. And then we evolved to fuzzing, that is a dynamic approach that allows you to spot harder vulnerabilities. But fuzzing is a kind of a naive approach or non-directed approach or non-targeted approach that basically is going to try multiple attempts, different attempts in a brute force way, even though somehow guided by coverage. But it's still some brute force approach to find bugs, so there is no guarantees. And at this point, you might be wondering, oh, but is this the best that we can do? Can't we do something more targeted, more a smarter approach to do that, to deterministically find vulnerabilities and constructions? And the answer is yes, there is a way of doing that, and this way is symbolic execution. That's the topic of the class today. So today we're going to cover how do we find vulnerabilities automatically, how do we find constructions automatically, crashes and other issues, by modeling the application symbolically. So let's dive into it following our standard flow of giving definitions, presenting a tool, and then going to a demonstration. So when we talk about symbolic execution, as the name says, what we're talking is about making computations not on actual values, but on symbolic values. So basically what you are trying to do is to take the application that we have, the binary that you have, to another representation, more specifically to a math representation. So the program that you write in the end is the actual implementation of an algorithm. An algorithm is a series of steps. So an algorithm is in the end a math concept, a math object, a math artifact, right? So you write this in a programming language, this becomes a binary. So the binary is somehow another view of the math modeling. What we do in symbolic execution is that we get the binary, in general, a binary that we don't know, that we don't control, that in general that's the case. That's why we operate in the binary. And then we take this binary back to the math representation. We lift the binary. So basically, we get this binary represent as a math, and we operate in the math. And then when we are operating in the math domain, we can ask math queries, like if such a construction exists, like if a given buffer overflow exists. So right now, we execute the application to not on the concrete values, the actual inputs, but we execute the application over symbolic values, representation of what the application do. And then this is going to become a math equation, a math formulation, and then we are going to try to resolve this math formulation to resolve if something exists or not. To give more concrete examples, let's talk about the difference between concrete and symbolic execution. So when we talk about concrete execution, we are talking about, as the name says, concrete values, the actual values that you pass. So when you have an input, the input is 1, 2, 3, 4, A, B, C, whatever is the input, this is the concrete input. So when you have if then else construction, and you ask if x is bigger than y, what you are comparing if it's the actual value stored in x is bigger than the actual values compared in y. Doesn't matter if there might be other alternative. If x is 5 and y is 3, 5 is bigger than 3. There might exist the opposite case. There x might be 3 and y might be 5, but this doesn't matter for the concrete execution. The concrete execution, that's the execution that we normally do when we run our application, we are doing a concrete execution. We are seeing the actual value that we have in the variable, and then we execute it and take this path. So we always execute a single path for a single input. That's the idea. But as you can see, as you can imagine, well, there is a bigger abstraction level, because if you think that x and y are variables that can host any value, not only 3 or 5, we could model this in a bigger way, saying, oh, there is something here. Every time x is bigger than y, I go through this path. Not only when it's 5 and 3, but also when it's 6 and 4, when it's 7 and 1, when it's 10 and 9. So every time x is bigger than y, I go over there. So there is a more general things, a more general construction over there. So if we treat the variables as actual symbols and not on the actual values, what we are deriving is not simply an execution path, but a property of that path. Every time that property holds, we are going to traverse that path. And that's the idea of symbolic execution. So instead of computing the actual variables, we are computing over symbols. So if we have an application that first gets a value, then sum ones, then sums one, we are going to do a concrete execution saying, well, if your input is 1, I'm going to sum 1 and give him 2, and sum 1, give him 3. That's the actual concrete execution. But if you are doing symbolic execution, what you are understanding are the properties, the relations between the multiple instructions in your application. So you're getting an initial value, x, and then sum 1, x plus 1, and then sum 1 again, x plus 1 plus 1, x plus 2. So whatever the value, the initial concrete value of xe is, I don't know that in the end I have x plus 2. So if I concrete execute the application, and if I ask, oh, can the output of this application be 0? Well, if I do this in a concrete execution, for instance, fuzzing is a concrete execution, the answer is, I don't know. All that I can do is to run the application over and over and over again, and if I get an output that is 0, I can answer, yes, the output is 0, is possible. But if I never get the 0, I can never say that the output 0 is possible. All that I can say is, I never seen this before. That's the case of vulnerability. If the fuzzer finds a vulnerability, we can tell, yeah, this application has a vulnerability. But if the fuzzer never finds a vulnerability, we cannot say that, oh, this application is free of bugs. All that we can tell is that, well, we haven't observed a vulnerability so far. But if you are doing symbolic execution, we can make bigger conclusions, because we can say, well, this application is modeled as x plus 2, x plus 1, x plus 1, x plus 1 plus 1, so x plus 2. So whatever the input is sum plus 2, right? So these allow us to conclude that if the value of x is different than minus 2, or if the x value is over, the input is over larger than 0, if you have this restriction, this program for sure will never exhibit the 0 output, right? That's the idea. So we can math prove that, right? And that's the idea of symbolic execution. We model the application in a way, and then we can ask a question like, does this program has a vulnerability? And then it's going to tell you deterministically via the math formulation if yes or no, right? How do we do that? Well, basically, we have to model, for instance, is it possible from a buffer to achieve this other region? That would be a buffer overflow. So if the symbolic execution tells, yes, there is a solution, there is an input, an x value that given this buffer goes to another place, the symbolic execution is telling you that, yes, there is a no buffer overflow. But if the application tells, no, there is no value of x, there is no input that allows you to go to this direction, to this region, then the application is proving you, telling you that for that region, there is no buffer overflow at all in your application, right? So it's much more powerful. How we do that? Well, basically, we actually execute the application. But every time we see a new instruction, we don't actually compute the value of instruction, but we derive a new math rule from that instruction. So we actually execute this application that you're monitoring, instruction by instruction, and every instruction that we see, we lift this instruction to a math representation, and we append it to the previous restriction. So initially, we take an input. Our math representation is get the value x. The next time we sum plus 1, our restriction becomes, x plus 1. And then we execute the next instruction that sums 1 again. Our restriction becomes x plus 1 plus 1. So we keep doing. So at the end of the application, we will have traversed the entire program, the entire application that you are monitoring, and we are going to have a complex math formulation of the program. And then we'll have to solve this math formulation, right? That's how it works, right? That's why it's called symbolic execution. So as you can imagine, compared to fuzzing as we are doing, there are pros and cons, because the pros is clear. It's a deterministic way. It's targeted, and it covers multiple paths at the same time. As I said, it's not only about value 5 is bigger than value 3. No, it's every value x is bigger than value y. It's going to allow to give you this type of conclusion. So there are guarantees that it's going to find invariants and general things, while fuzzer do not have concrete execution, do not have that. But on the other hand, there is always a trade-off. There is a cost. That is basically, we are going to come up with a very huge math formulation in the end, and very huge, because if we have like two applications, x and y, it's very easy. We have 4 combinations of x and y, right? But if we have an application with multiple variables and multiple bytes and multiple inputs, very large strings, and everything is symbolic, we are going to end up with millions of math variables, right? So you have to solve the polynomial of millions of variables. And this is not doable. This is called as the path explosion problem, because every time you have a branch, you are doubling the number of paths that you have. So you're doubling every variable that you have, you are doubling, and then at the end, you are going to end up with millions of variables. And we don't know how to solve the problems with millions of variables. So in general, what we find is just an approximation of the solution. So once again, ideally, this technique can solve the problem, given infinite time and infinite resources. But since we don't have infinite time and infinite resources, we are going to find an approximation of the result. So in the end, it's a probabilistic thing comparable to the fuzzer. Because in the fuzzer, we know how to solve the path because we can actually execute it, but we don't know how to select the path because it's concrete, so every time we have to execute a different path. To compare with symbolic execution, it's exactly the opposite case. In symbolic executions, we know exactly how to choose because we choose via method, but we don't know how to solve the problem in the end. So they are the dual, the inverse of the other. So they are in the same category. In general, fuzzing and symbolic execution are complementary solutions, right? To give a more concrete example or a more symbolic example to make the joke here. So in general, if you have 2 variables, x and y, when we do concrete execution, we are reading the actual value. So x means 5, it stores the 5 value, and y stores the 3 value. So if I'm at this point here, at what I'm showing, well, 5 is bigger than 3, the execution is going to proceed via here, right? That's what's going to happen. What I'm proposing is we are going to model this decision symbolically. So this decision, instead of being this concrete value, is going to be modeled as the condition of the if is x bigger than y, right? And then at some point, when we need to actually decide, and then we replace with substitute here, what is x? Well, x is equal 5, y is equal 3, so 5 is bigger than 3 as it was expected. But notice, these, although they reach the same result as they should be, of course, it's the same application, both should be correct. The way of reason about this is different. One, we are going concretely saying 5 is bigger than 3. The other one, we are going to go symbolically, and then we are saying, I need a combination of x and y values such that x is bigger than y. So this discovers that this region here is reached by 5 and 3, but also by any other values that satisfies this condition, 6 and 4, for instance. So it discovers all possible ways to reach this condition, right? So that's the idea. And then you say, okay, how is it useful, right? So right now we are just discovering two different ways, one more complicated than the other, to find that 5 is bigger than 3. I can't see how this is useful for vulnerability. Okay, so let me give you another example. So let's keep analyzing this program, but now we see that there is a return here in the end, x plus 5. And then now I'm going to stop here, like if it was a breakpoint. I'm stopped here, and I want to know what are the possible values that can be returned here, right? That's the question. Right now, I don't have the concrete values anymore. On purpose, I'm removed. So I don't know. I just know that I have a variable x that I'm going to read a value, and I have the y value. So based on two values that I don't know which ones they are that I'm going to read, I'm going to make a computation, and I'm going to return x plus 5. So my question is, what is the value that I'm going to return here, right? And then, basically, depending on the values, we are going to traverse different paths. So we can model this region. So this model can be, if x is bigger than y, x is x plus 2, and then x plus 2 plus 5, right? So x plus 7. Or if x is smaller than y, x is x is minus 2, so x is minus 2 plus 5, x plus 3, right? So these are the two possible results. So if you math model these things here, you are going to come up that a representation of this excerpt of the program R is this expression. If A bigger than B, then the result will be A plus 7, whatever value of A. This is an invariant. Whatever value of A, this will be the returned value, right? Or if A is not bigger than B, so it's smaller or equal, then the value will be A plus 3. Whatever value of A, it will be A plus 3. So I derive two conditions. So these are the two conditions, the two ways this program can operate. And then what I'm looking for, is there a vulnerability? So imagine, this is the function that authorizes me to do something. And I want to discover if this function returns a given value, if x plus 5 is equals 10, right? Or equals something, or positive, or it's true, or is it, if x plus 10 is equal a given value, the access to a function is authorized. And if x plus 5 here, x, whatever value is returned here, is false, is negative, is equal 0, is whatever the k value that is your target, the access is not denied, is denied. So I want to discover what are the x and y values that I need to provide to this function such that the returns grants me access to the function. So what I can do is I get this function, this entire function here, say, oh, this function returns this. And I say, these functions should be true, or should be 3, or should be 10, or should be x, y, z. That doesn't matter. So this function, this equation, this function becomes an equation because I say, this function has always this property, and what I want is this property to be access guaranteed. So I make this function to be guaranteed. So it's basically the same idea that I have a polynomial here to solve, in this case, a Boolean expression, and then I have to make this expression to look like this. If it was a polynomial, what I'm asking here in the end is, what are the roots of the polynomial to get this value, right? So here what I'm asking is, what should be the input values of A and B such that this expression or this expression, one of these sides, allows me access guaranteed, right? And then I can solve the expression. This expression is likely small enough, and then I can get a value that satisfies the equation. For instance, let's suppose that access is allowed when this is bigger than 10, and then I can know, okay, if I select 10, A equals 10 and 5, and B equals 5, then their final value is 17, and 17 will be a number that allows me access the desired resource. So I discover input values that satisfy this, right? And the ones that do not satisfy as well, right? How do we use this to find vulnerabilities? Once again, imagine that A and B are input values that goes to the buffer. This entire expression is modeling your stack, your buffer. And then what I'm asking here is there values of A and B such that if I do that, the return value is overwriting the return value of the stack, such that the return value is achieving a given location, returning to a libc function. So basically, I force the equation to be like that, and I try to resolve. If the equation fails, means that this function is not possible to overflow to get this location. But if I succeed and find the values in A and B, it means that when I fill the buffer with A and B, I'm going to reach that location, and then the vulnerability location is found, right? That's how it works. So this is why symbolic execution is so nice. It's so precise, right? Hope you have understood how symbolic execution works, and let's go more practical, more hands-on. Once again, there are many tools for symbolic execution. The one that I chose to talk about here today is Angr. That's one of the most popular ones. But once again, you can try to do this in your project. You can try symbolic execution of your projects to see what you can discover about them. Angr is a good candidate, but you can use anyone. I chose to talk about Angr because it's written in Python. It is very easy to do. It's very simple. And basically, it supports a variety of binary, and it does all the magic for you. All that you have to do is you give a binary to Angr, and Angr is going to interpret the binary, make the math modeling, and provide this expression to you already. And Angr can also solve the expression for you. So Angr is, in fact, a big framework that does all these things for you. So if you understood the theory, basically now you can just get Angr and apply it to your problem. That's very simple. To apply, you need to know a few concepts. Of course, in general, I give a course about Angr and so on. Here, I'm going to focus on two key concepts. The first one is the state. That is, as the name says, is where you are in the code and what are the values of the variables at that code. For instance, when you are here, initially you have to define what is the state. So if you give concrete values to here, say, oh, state starts with 5 and 3, what's going to happen is a concrete execution because there is no choice, right? You're giving values. But if you are saying, oh, the initial state is X is a symbolic variable and Y is a symbolic variable, what the Angr is going to do is a symbolic execution. So depending on the input, depending on the initial state, symbolic or concrete, it does a concrete execution. And notice, here I have a state, that is, I have no constraints. X and Y at this point might be anything. But when I'm here, notice I'm in a given state, because to be here, it's only possible if X is bigger than Y. So I have one state here, I have a different state here. And if I'm here, I have a third different state, because at this point, to reach here, the only way to reach here is if X is not bigger than Y. So I get here. So states are the set of variables and the set of restrictions that you have in each point of your application. So this, as you can imagine, is very important to control what you are doing and where you are in the application, right? So this is important. Hooks and sync procedures are important, but we are not going to cover them in our demonstrations. This is a more advanced use that you can use for the project. I can talk about that later if you want, especially in the checkpoint classes. But I would like to talk about exploration. That is the idea that I presented for fuzzing data. Our applications can be represented as a tree. And there are different ways to explore a tree, right? In general, there are two big ways. That is in breadth, BFS, or in depth, DFS, right? So Angr can explore the application in these two ways, and then you can control how you explore. And then you can also control when you stop the exploration, because you can explore until the end of the application execution, or you can establish that when I reach a given point, I can already stop. For instance, if I'm just looking for a crash, the first crash that I find, I already stopped. But the other technique might be, no, I want to explore everything. I want to explore all paths to find all the crashes, right? So these are basically where you start and where you are going and how, right? So these are the two most important things. How do we put it to make it work? Well, there is the Angr syntax, so there are many things that are required. Once again, I'm not focusing here on the syntax of the Angr functionality. You can check documentation, you can ask ChatGPT. That's not the purpose. The purpose here is to teach you the concepts, right? And of course, you have to import Angr, you have to create an Angr project passing your binary here. Once again, the syntax is basically always the same, you just check documentation. The important thing is you give a binary, and then after you give a binary, you are going to start the application from a given entry state. So if you remember, we are talking about states, right? And then I mentioned that one of the things is the state here. So you have to specify where you are in the beginning. What are the values that you are going to pass? So in this code is empty state. There is no variables being created, there is nothing. So this code is starting from the zero, right? And from the zero, you're going to create a manager. Once again, this is Angr syntax that you can learn. The important thing is explore, the exploration strategy. So if you go back here, say, how do you want to explore? And until when do you want to explore? So for the how, here we are always using Angr's default. I'm not asking you to learn any new different things. So you can go with the default configuration. The default are going to work for the assignments, right? But we are telling that, oh, I have to explore until we find, and what we need to find, for instance, the welcome word. So I'm going to execute symbolically this program until I find until the output is welcome. I know the output because there is the POSIX here dump, and then we have the one. So if you know the file descriptors in Linux, you know that the 0 is the standard input, 1 is the standard output, and 2 is standard error. So basically, this code is checking if there is the welcome string in the descriptor 1 output. So basically, notice that in GDB, we have to give the breakpoint, and then you have to say, hey, GDB executes until this address. When we do symbolic execution, we are much more flexible because this is like a breakpoint, but we don't have to say what is the address. We say the actual result. We say executes until welcome is printed on the screen. Because when welcome is printed on the screen, I know that I'm in the right path. The binary is welcoming. If I find the other paths, I'm in the wrong way because the binary is not welcoming, right? So this works as a kind of a breakpoint, but it's a much more flexible one because I don't need to know the address. All that I know is execute until I get it right. It's almost magical, right? So you say executes until the output is what I'm looking for. And this is very good, very flexible. And once you say that, oh, this is the address. So when you are here, the found is the address. It's going to tell, hey, now I'm stopped here, like in your breakpoint. And this is the found location, the found value here. And then what you can do is, as we have seen here, after we model, we solve the expression, and the expression gives concrete values. Same thing here. We model this an expression, and after we model the expression, we give concrete values that satisfy this equation. These values are not unique. It's like this polynomial has many roots, right? So this is one of the roots that satisfy the equation, but then you get it. Here is the same idea. Here, when you are here, you have this is going to model, explore is going to model this as an equation, as a Boolean expression. When you are here, you say, hey, give to me a concrete value that satisfies this equation, and this is going to give you a solution for the problem, right? So this is a very easy way in a few lines of code to solve like a crack me problem when you have to discover which input to pass to the binary to give the welcome word without doing no debugging at all, just letting the execution to proceed because we are doing a symbolic execution. We are executing the math behind the application, right? For what we can use this symbolic execution? Once again, for everything that we are talking in our course and much more, We can do this for patching, for reverse engineering, malware analysis, finding bugs, vulnerabilities, the corner cases that were not spotted by static analysis and fuzzing, and more specifically for vulnerabilities like buffer overflow. Once again, what we could do is explore until we find a crash, a given error message, finding until I get segmentation fault. So this is going to explore the entire program, and then the solution is going to give and say, hey, in this address, if you put these values, there is a segmentation fault, right? And then you have to get these values and investigate and write in the exploit. Once again, like fuzzy, it does not automatically exploit things for you, but it tells you the region the exploit is. It tells what is the value of the buffer to cause the buffer overflow. After that, you have to write the exploit as we have been doing in previous classes. So, going to the conclusions, once again, there are more advanced cases, but I would like to focus on the fact that we were evolving, right? So we had static analysis that has some drawbacks, and then we had fuzzing, that is a dynamic analysis approaches, but it is less targeted. And then we finally went to this very targeted approach that is symbolic execution. Symbolic execution is another category than concrete execution, whereas in concrete execution, we execute the actual value. In symbolic execution, we lift the binary representation back to a math representation, and then we try to solve the equation to identify what are the inputs that the application is expecting, right? Ideally, if the instance of this equation is small, we can solve this deterministically. If this is too big, there is a path explosion, millions of variables. We don't know how to solve this efficiently. We can find approximations, and in general, these approximations are good enough. And you can use Angr to find this. So to give you concrete demonstrations, let's go to the hands-on part of our tool. So I'm going to run Angr in a Docker, as you can see here. So you can download the Angr Docker. It's pre-built, so very easy to install. At this point of this course, probably you are used to this Docker and to this kind of things. All the assignments are very, very similar in this sense. And here I have some crackmes, as we call, right? Basically, let's see, where is the crackme? Oops, I need to mount from the right place. Yes, now we are at the right place. So we have some crackmes here. Let's see, how do I show a crackme to you? For instance, I have a crackme that is a type of application that is going to receive an argument in argv, right? And it's going to check for the password. If the password is the value that I'm expecting, this is going to give access granted. Otherwise, it's going to give access denied. In here, we have the source code. You're observing the source code. But in most cases, we don't have the source code. All that you have, it's just like the crackme itself. And then you have to run the crackme and try to find the solution. And then you're going to run. It's going to say, oh, crackme password. And then you're going to try 1, 2, 3, ABC. And then the password is always access denied. So one solution to that is maybe you go to GDB, set breakpoints, and try to discover how it works. But the other solution is to do symbolic execution, right? Symbolic execution, we can do something using Angr. So basically, we import Angr, we create the project, same things as we saw, and I'm doing something interesting here. I'm creating an input variable, an input string, and I'm saying that this input string that has given number of bits and bytes is a symbolic. So this is a bit vector symbol. So basically, this is a symbolic variable, right? And when I started running the application, when I say, what is the initial state? If you remember, from where do I start? I'm saying, I'm going to start executing like correct me, argv0, the name of the application, and argv1 is symbolic variable. So instead of passing the concrete variable, crack me 1, 2, 3, crack me ABC, I'm passing crack me symbol. So what the Angr is going to do is to execute the entire crack me application over the symbols. And I'm going to explore. We mentioned about that. We explore, we're executing until what? Until granted appears in the output, right? So I started from a symbol. This is where I'm starting. I'm starting from a symbol, and this is where I'm reaching. I'm reaching granted. And then you're going to say, Angr, find a way that my input, my symbol, leads to the path that has access granted. And once you find it, solve the equation to tell me what value input string should have to reach the granted, right? And then we solve it using Angr. We're going to solve. Angr is going to run model and going to tell us in the end the same. Hey, the correct password is correct password, right? Because that's exactly what we what had in the beginning, right? We are doing the comparison. argv is expected password, right? But this case is very simple. What if we have a more sophisticated application? So I can show you crack me .c. So in this one, the check password is more sophisticated. I still have a lot of checks access denied before having the granted, but you can see I have a much more complicated validation, right? A validation routine. So how to discover it if all that I had was the binary, was like, oh, crack me. And then I'm going to put things, including correct password, and it's going to say access denied. How do I do that? Once again, we can use the same idea to solve, saying, I have an input variable, I want to execute until granted. For me, doesn't change anything. It's the same thing, right? It's the same script, right? Same thing that I was doing before. Because doesn't matter. What matters is the program, whatever it is, will be represented as a math entity, and then it will be solved. So if I ask it to solve it, this crack me, it's going to execute, and then it's going to tell, well, I discover that if your input is ABC123XY, this will allow you to access the granted. And then we can test if it's true, because if I put correct password for this one, it's access denied. But if I give ABC123XY, it is exactly granted. So it takes me to where I want, right? So this is how symbolic execution works. In this case, it's pretty fast because the application, the program is small. If the program is too big, well, we need to start to make approximations because there might be the path explosion problem. If you learned that, well, we can do the assignment for symbolic execution that basically repeats what I did. So create applications, at least one application, that has a complicated case that you have to solve, multiple if then else. The more you put, the more complicated the condition, the better, the more realistic it is. And then you use Angr, symbolic execution, to find it, to solve the actual input that leads to that specific path among multiple ones that you have. So basically, repeat the crack me exercise that I did, hopefully at a much larger scale, much more interesting case. Right? That's what we have for today, and thank you.